topic we're looking at today is more chain rule, some other rules, some tangent, cotangent, secant, cosecant, so tangent, and then the reciprocal trig functions, but also these wonderful nested chain rule problems. So I love me some composite functions. These nested chain rules are composites within composites. I'm so happy. So remember, section 2.2, there was the sine becomes cosine, cosine gets replaced with negative sine. We also have these other rules for trig functions, tangent, and then all the reciprocal functions. One thing that can be kind of nice to remember is that if your trig function has co in it, so cosine or cotangent or cosecant, so these three, the derivative will have a negative. Cosine becomes negative sine, cotangent negative cosecant squared, cosecant becomes negative cosecant cotangent. The others remain positive. So what would be a video and some fun without a proof? So prove that tangent equals secant squared. So we'll do a quick quotient property. The derivative with respect to x of tangent, let's rewrite that as sine of x over cosine of x. So do a little quotient property, low d high over high d low minus the over low squared. So low d high cosine d high of is cosine again minus high d low. Derivative of low would be negative sine x all over low squared. So do some simple simplification. Cosine times cosine, cosine squared, minus sine times negative cosine. So sine times negative sine, negative sine squared, so we're minus a negative sine squared, be plus a positive sine squared, all over cosine squared of x. Now thinking back to trig and precalculus, we have the numerator cosine squared plus sine squared. That's the OG Pythagorean theorem. Just 1 over cosine squared of x. 1 over cosine is secant, so 1 over cosine squared is secant squared of x. So kind of a short proof, very similar to what we did last year in chapter 5, doing those trigonometric verifications. So take a look at example 5 and example 6. I'm going to try those out, check answers with my complete notes online. So doing general trig functions with the chain rule, look at this first one. We can say d dx sine of u. U is some function, okay, whatever it is. It's whatever. It's x or it's 5x to the 4th minus 3x squared plus 2. Or it's tangent squared, sine of tangent squared. So sine of something. Doing chain rule, remember, sine is the outside, u would be the inside. So derivative of outside, sine gives you cosine, leave the inside alone, so it's just u, times derivative of inside, so times u squared. This can be generalized to all 6. So whatever you have, chain rule, derivative of outside, leave inside alone, times derivative of inside. So let's take a look at these kind of three problems right away. We have sine of 2x, sine, let me get the box here. Alright. Sine's going to be outside. 2x is going to be your inside. So to put that all together, again, write things out to start, but in time you want to be able to do these mentally. So kind of think ahead, what would we have if we did the generalized chain rule? So derivative of outside, sine gives you cosine, leave the inside alone, then times derivative inside. There you go. Cosine of 3x minus 1. Again, we have the outside, cosine. We have the inside, 3x minus 1. So do your generalized chain rule. Sine of derivative of outside, so derivative of cosine, is negative sine. And to leave the inside alone, times the derivative of the inside, so derivative of 3x minus 1, so times 3. Look at the example C. Again, try to look at that, mentally figure it out. Kind of looking at this, so secant of 4x. The secant rule up here. So you'd have, kind of looking back and forth at the formula, I already have secant of 4x, so secant of 4x and tangent of 4x times u prime, so times derivative of 4x, 4. There we go. So kind of using that chain rule generally, again trying to move from writing everything out to moving faster, doing it mentally, okay? Again, practice makes better. Don't go like 100 miles per hour right into it. Ease into it, write down what you need to write down, but keep trying to write less and less. Now, my favorite part here, the nested chain rule. Problems that require repeated use of the chain rule. So functions plugged into functions. So example A, y equals sine to the fourth of 3x. So this is the same as sine of 3x. All raised to the fourth. So you see how we have multiple sets of parentheses. We have sine plugged into a fourth degree function, a quartic. Then 3x, a linear, plugged into sine. So there's multiple layers to this. Gotta peel back the layers one by one. So let's go ahead and do the first layer, the sine to the fourth. So overall, the fourth power, let's do that. So bring the 4 down. That's now to the third. Leave the inside alone. So there's our first kind of chain rule. When we multiply by derivative of inside, we have to do chain rule again. So now the inside, coming right here. So inside, that's sine 3x is sine of 3x. So sine is the outside, 3x is the inside. So derivative of sine is cosine. Leave the inside alone, times derivative of inside 3x. So times 3. So we had right here kind of our first chain rule. And then when we went to do derivative inside, derivative of sine 3x, we had another chain rule that we had to do. So multiple layers, do one layer at a time, kind of work outside in. The fourth power to the sine, then to the 3x. Let's take a look at example B also. Let's kind of rewrite this. As a secant, I'm going to do a couple of rewrites. Secant of 1/2 x. I don't want that. Of 1/2 x to the 1/2 power. Square root becomes a 1/2 power. So let's go for do y prime. So doing the 1/2 power first, that's the overall function. So bring the 1/2 down. Decrease the 1/2 by 1, so 1/2 minus 1, negative 1/2. Leave the inside alone. And then we gotta multiply by derivative of inside. But hey, the inside, another chain rule, a secant of 1/2 x. So let's evaluate that. Secant is our new outside or overall. 1/2 x is our new inside, okay? So times secant 1/2 x, so kind of looking up in my formula at the top of the page. Secant is secant tangent. So secant of 1/2 x, tangent of 1/2 x, times derivative of 1/2 x, so 1/2. So right here, had my first chain rule. Then right here, I had my second chain rule. If I wanted to clean that up, let's say it's a multiple choice, you got to do some algebraic manipulation. The 1/2 and 1/2, those are paired together to become a 1/4, so let's put a fourth in the denominator. The secant 1/2 x to the negative 1/2, move that to the denominator and make it a square root. So secant x over 2. The secant 1/2 x tangent 1/2 x, that can move to the top of the fraction. So secant, 1/2 x, I don't want that, x over 2. Let's go back to the x over 2. Tangent of x over 2. Now this is where the multiple choice can get tricky, because you have a secant x over 2 in the top, a secant x over 2 to the 1/2 in the bottom. Those could be cancelled out. So now you have a secant x over 2 to the 1/2 in the top, so a square root, tangent x over 2, all over 4. So again, FRQ could have this, multiple choice, they might want you to reduce. Don't do that, okay? Example C, take a look at that. Check my completed notes online. And then let's look over here. Examples 9, 10, 11. Very complicated chain rule problems. I say complicated because, as always, there's multiple rules to use. Each of these requires chain rule at some point. So like example 9, overall x squared times root 1 minus x squared. Overall, that is a product rule. So you're getting the puzzle pieces for product and putting that puzzle together. Some of those pieces might require the chain rule. Example 10, x over cube root x root of 4. Overall, that is a quotient rule. Now doing your low d high minus high d low over low squared, getting those puzzle pieces, putting them together. Some of those puzzle pieces might require the chain rule. Here overall, we have a power and the chain, and then to do the chain, the derivative of the inside, that's going to require quotient. I mean, so they're, I say complicated, because there's a lot going on. You got to kind of keep track of your work, stay organized. But all the individual pieces you can do. Just got to put them all together. Take a look at those and check my complete notes online.